All right, y'all, let's talk about compound probability. Now, compound probability has to do when you're trying to find what happens when one or more events are happening, what happens when they're affecting each other, what happens when they're not affecting each other, and what does that do for the overall probability. So let's talk about our types first. What we've been working with already is one trial. When you're finding the probability of just one trial, it's simply called an outcome. So this is when I'm talking about that bag of marbles again, and I'm saying, hey, I just want to pick one marble out of it and see the probability. If I want to somehow do one trial and compound, it can be expressed as saying we want to choose from A or B. In the case of my marbles, that's saying, okay, I want to see what is the probability of one try. Am I going to get a red or a green? If I want to find that probability of that one try, I'm going to go ahead and I'm going to add both of those probabilities together. So if I have 5 red marbles and 2 green marbles, I have a probability of 7 out of my total. Okay, so that's just if we're doing one trial, if we're working with a compound probability on one trial. Let's talk about the compound probability on one or more trials. When you're finding the probability of one or more trials, it's called an event. So the difference between this one, an event, and this one, an outcome, is an outcome again is one try. What's the probability of getting red or green on one try? This is the probability for multiple tries. This one can be expressed as A, then B, A, and B. So I could say what's the probability of getting a red, then a green, or a red and a green in my 2 tries, okay? To find this kind of compound probability, we're going to multiply the probabilities together. So I would take the probability of the first one, pulling a green, and multiply it by the probability of the second one, pulling a red. However, there are 2 different types of probabilities here that we're going to need to account for. First is talking about an independent probability. When you think of independence, you probably think of somebody who doesn't need any help from anyone and can do it all by themselves. It's kind of like that here. Independent events do not affect each other. One does not change the outcome in the other. They're independent, they are completely separate from each other. So when we are taking the compound probability of independent events, we often represent that by saying we are picking with replacement. When we are to replace something into our sample, it does not alter or change our overall probabilities. Then we have dependent events. When someone is dependent on somebody else, they need that other person to help them out. They need that other person to affect them. So dependent events do affect each other. Independent do not, dependent do. We often represent this by saying without replacement. So if I pull from a sample and I do not put that thing back, I have altered the overall total, which has altered the probability. So dependent events are going to change from try to try. Independent events are not. So let's put this all together down here. We're going to talk about the differences between single probabilities and compound probabilities here. So let's look at example 1. In example 1, we have a box of crayons. There are 5 red crayons, 3 yellow, 6 blue, and 2 green, and we want to find the following probabilities. Now, hopefully you remember from our previous videos and our previous notes that in order to figure out probability, you always got to figure out the total. So first, we're going to go ahead and add 5 plus 3 plus 6 plus 2. We're going to figure out there are 16 total crayons here. Because no matter if this is a single probability or a compound probability, they are always going to be out of the total. All right, let's start with A. The probability of picking a green marble. Now this is just one try. Just one try, one chance at getting a green marble. So we go back to our old ways of probability. All right, there are 2 green out of 16 total. So on one try, we can get 2 out of 16. If we want to reduce that fraction, we can totally write that as 1/8. So I have a 2 out of 16 or a 1 out of 8 chance on one try of picking a green marble. All right. B. All right, this one says, what's the probability of not picking a green marble? Well, in a previous video, we started talking about not. Not is our complement event, and we had a rule. So remember, to find the not, to find the no, you simply take the total and you take away the yes. So in our case, the total amount of marbles we have is 16. And we are going to take away the yes that we found up here. We found 2. So we're going to do 16 minus 2. That gets us there are 14 marbles that are not green out of 16. So our yes is 2 out of 16. Our no is 14 out of 16. Together they should add to get your total. We could reduce that if we want, and we can write that as 7/8. All right, so both of those have been single probabilities, what we've already been working with. Let's move on to our compound. Okay, be careful with the wording in part C. The probability of picking a green or a red marble. So check our wording up here, right? We said there was 2 different kinds. There's an outcome when you're just trying to find the compound in 1 try, and an event when you're trying to find the compound in 2 tries. Our key word down here was or. Or, if we look back at our notes, is that 1 try. So what this problem is asking us is what's the probability of getting a green or a red marble just in 1 try? So remember our rule from above. If we're just trying 1 try, we're going to take the total of green, which is 2, and we're going to add it to the total of red, which is 5. So our total here would be 7 out of 16. So this is our compound on 1 try. All right, let's go to the next one. The probability of picking a green then, there's our keyword right there. So then brings us to our multiple events here. We are doing multiple trials here, seeing what happens when I pick more than 1 time here. So I'm probably picking a green, then a red marble, which means I'm trying for a green on the first try, then I'm trying for a red on the second try. But the other key thing we have to check here is it says with replacement. What this means is I'm going to try for a green. So I'm going to reach into my crayon bag, I'm going to pull out a green, and then I'm going to put it back. With replacement means that they are independent events, meaning once I pull the green one out, I take a look at it, I say, I don't actually want this one, and I put it back in, not changing the overall total. So to do this one, we start with our green pick. So the probability of green, as we expressed before, is 2 out of 16. Then we're going to put our multiplication. And now we're going to do our red marble. Now remember, I haven't altered anything, so it's still out of 16 because I put that green one back. And our red probability is 5 out of 16. So this represents our first pick, and then I put it back, and this represents our second pick. So green, then red. So when we multiply that together, we get 10 out of 256. If we want to reduce that, that goes to 5 out of 128. That is our independent probability. Let's check out our dependent. Almost the exact same situation, right? It says green, then red. But right here it says without replacement, meaning when I take the green crayon out, I keep it out. And when I keep that green crayon out, the overall total that I'm picking from changes. So it's going to start the same. On my first pick, there are 16. And out of those, there are 2 green ones. All right, I'm going to multiply it to my second pick. Now here's the problem. Once I took this green one out, the overall total has decreased to 15 because I took a green one out. So our second probability will be the 5 red out of our new total 15. This is dependent because the first one affected the second one. So I'm going to go ahead and multiply those together. I'm going to get 10 out of 240, or in other words, 1 out of 24. Okay, so again, keywords here when we're talking about compound probability. If we're just doing it in 1 try, we're often looking for the word or, and we're just adding those totals together. If we're doing it in multiple trials, we're looking for the words then and we're multiplying it together. But we also have to pay attention. If it says with replacement, nothing's going to change, it's independent. If it says without replacement, something's going to get changed, it's going to be dependent. All right, let's talk about our next thing with compound probability. Go ahead and flip to the next page. All right, so we already have some rules in our tool belt. We have the addition rule for unions. We have the compound rule. Here's your next rule you're going to star. Go ahead and star that one right there. This is called your multiplication rule of independent events. This can do two things for us. First thing it can do is it can help us prove if events are independent. Because if we were to take the probability of event A and multiply it by the probability of event B, if they are actually independent, we'll get the probability of and. We'll get the probability of the overlap of both of them. We can also use it just to find any missing probabilities. If we know they are independent, we can plug in two of them to find the third. So let's see that in action in two different ways. So example 1 is about proving independence. Before we start though, let's remind ourselves, when we are looking at our Venn diagram, the probability of event Y is this entire circle, and the probability of event Z is this entire circle. The and is what's represented in that overlap in the middle. So here's what we're gonna do. We're gonna start with probability of Y. So the probability of Y is this entire circle. It's not just 0.4. It's 0.4 plus 0.12. So the probability of Y is 0.52. The probability of Z is this entire circle, so it's not just 0.3. It's 0.3 plus 0.12, so it's 0.42. So now that we have the probability of the separate events, we can use our rule of multiplication of independence up here to figure out if they are independent. Here's how we do it. The rule says that the probability of the first one multiplied by the probability of the second one should equal the and right here. It should equal that middle. That's the question at hand. We're gonna double check this and we're gonna see, okay, 0.52 times 0.42. We're gonna type that in, we're gonna see, oh, that is definitely not 0.12. And because that's not true, these are not independent. Okay, so that's the first way that this rule can help us. Go ahead and pause the video right now, guys, and try example number 2. All right, hopefully by now you've tried example number 2, and hopefully this is what you found. First, you started with the probability of Y, remembering that it's this entire circle, so it's 0.12 plus 0.08, which gets you 0.2. Then you found the probability of Z, again, remembering it's this entire circle, so it's 0.32 plus 0.08, which gets you 0.4. And then you used your multiplication rule of independence to test it out. You said, okay, the probability of the first one times the probability of the second one should equal their overlap, should equal what's in the middle. And that's what you asked yourself. So you picked up your calculator, you plugged it in, and you figured out, yes, that's totally true. These are independent events. Okay, so that's the very first way to use our brand new rule here. It's just to prove if events are independent. The last way we can use it is when we know events are independent, it can help us find the missing probabilities. So one last problem here for us. All right, so let's read example 3. Suppose a person who is having 2 surgeries performed at the same time by different operating teams. Assume, unrealistically, that the operations are independent. So right here, they're giving us the go to say they are independent. Since they are independent, this rule totally works. So they are independent, so we can use that rule. So then it says, if the chances of success for surgery A, so the probability of A, are 85, or we're gonna put that into our decimal as 0.85, and the chances of success for B, the probability of B, is 90%, or 0.90, what then is the probability of A and B? Okay, so we've got 1, we've got 2, we've got to find it. Now, all we have to do now is our multiplication rule says we take the probability of the first one, we multiply it by the probability of the second one, and that's going to get us the probability of both. So when we go ahead and we multiply this, we get 0.765, or in other words, around 76.5% chance that both of them at the exact same time will succeed. All right, guys, that has been compound probability.